Hello, my name is Kyle Cherry. I'm a biology major from the class of 2019.
And my name's William Thompson. I'm a biochem major from the class of 2019 as well.
We will be working through Skill Builder from chapter 12.4, number 7 in the General Chemistry Workbook. You should begin by working on the problem yourself to see if you can get the answer. And pause the video now until you're done, and then we will go over it together. Alright, so problem number 7 here. For the graph at right or below, as we have now arranged it, first of all, what is the reaction order? So the reaction order refers to the rate of the reaction and how it relates to the concentration of A. So first of all the only information we have here is the graph of the natural log of the concentration of A versus time. So let's look at some examples of different order reactions and see the relationship between the natural log of A and time, because we can see here that it is linear, so knowing that, we can proceed. Alright, so in a zero order reaction, the rate of the reaction is independent of the concentration of A. It is just equal to a constant, and the graph of the natural log of A versus time does not produce a linear relationship. In a first order reaction, the rate of the reaction is proportional to the concentration of A, and we can see that the graph of the natural log of A versus time does have a linear relationship, as ours did from problem number 7. In a second order reaction, the rate is proportional to the concentration of A squared. And we look at the graph of the natural log of A versus time and see that it is not a linear relationship, leading us to believe that ours is a first order reaction, since we do have a linear relationship between the natural log of A and time.
Okay, so now, what is the initial concentration of A? This is part B. Well, let's see. We have our equation here, right? We have y equals negative 0.05 x plus 1.6094. But what does this mean? Well, if we look here on the y-axis, y is represented by ln of A. So we can write that down. Y is ln of the concentration of A, I should say. And on the x-axis, x is represented by t in seconds. So if we write that down, x is represented by t in seconds. So the initial concentration of A, we know, is the concentration of A that we start with, which is going to be right here. Now that occurs at t equals 0. So we're going to have to plug in 0 for t. So we have ln of A, which is how we're going to find the concentration, equals negative 0.05 t, which we are plugging in 0, plus 1.6094. Now we have to solve for A, of course, and the way we undo ln's is we raise this to the power of e, or we raise e to the power of the ln, and that cancels the ln function. Over here on the right side, this is just multiplied by 0, so this is going to go to 0. So we only have 1.6094 on the right. But since we raised ln of A to the e, we have to raise this to the e power as well. And so what we're left with is the concentration of A equals e to the power of 1.6094. And if we plug that into our calculator, we find that that is 5 molar. So what does this mean? This means that initially, at time equals 0 in seconds, the initial concentration of A is going to be 5 molar. Okay, part C. What is the half-life? So what we knew from part B is that the initial concentration of A was 5 molar. So what's the half-life? The half-life means how long it takes for half of A to be used up in the reaction, so we'll be left with 2.5 molar afterwards. Now this half-life is a constant amount of time that it takes to use up half of the reactant. So whether you're going from 5 to 2.5 molar, it will take the same amount of time if you were going from 10 molar to 5 molar. Again, it's just the amount of time that it takes to use up half of the reactant in the reaction. And so for this question, what's the half-life that we're talking about? We're talking about going from 5 molar to 2.5 molar, because that's half of 5. So again, with our equation, we have y equals negative 0.05x plus 1.6094. So now we need to figure out how long it takes to get to 2.5 molar. So we're going to plug that in to y, but we're not plugging in for y, we're plugging in for ln of A. But A is going to be 2.5 molar. And just like we did in the previous problem, we're just going to solve for t. So we have negative 0.05 t plus 1.6094. Now reducing this, we get 0.916 equals negative 0.05 t plus 1.6094. And so we can subtract 1.6094 from each side, and we'll get negative 0.693 equals negative 0.05 t. And now, if we solve for t, we get 13.86 seconds. Now what does this mean? 13.86 seconds. That means that it takes the reaction 13.86 seconds to use up half of our original reactant. So we'll have 2.5 molar after 13.8 seconds. And then after another 13.86 seconds, we'll have 1.25 molar. So after every 13.86 seconds, half of what is remaining will be used up in the reaction. And this is why the reaction slows down over time. So I hope this has helped you understand how to determine the reaction order from a graph, how to determine the concentration of any reactant based upon the graph and the equation given, and how to determine the half-life based again upon the graph and the equation given for the graph.